In this video, I'll be giving you a brief introduction to number theory, and as the name suggests, this has something to do and deal with numbers. Now, there are a lot of numbers that we've been using since we've been little kids. We have even numbers, we have odd numbers, we have prime numbers, we have natural numbers, we have happy numbers. Remember them? Remember, a happy number is the sequence here. We got 1, 7, 10, 13, and so on. So why do we call them happy numbers? Do you remember? A formal definition of a happy number is a non-negative integer that eventually goes back to 1, and that's called a happy number. Let's take an example. Let's take n equals to 28. Now, this is available on the list, so this is a happy number. But why is it happy? So what we do is we pick up the individual digits in the given number. So I'm just going to put 2 squared, and I'm going to take it and then 8 squared. So this value is 4, and this value is 64. So then I take the quantities, and then I get 68. And then again is repeat the same process. So 6 squared plus 8 squared, I'm going to get square it. I'm going to get 36, and I'm going to get 64. So I add these two numbers, and I'm going to get the next number, which is 100. Now I got 3 digits, and I'm going to repeat the process. It's going to be tricky with zeros. So we have 1 square, 0 square, plus 0 square, and this will finally turn out by addition, and it gets me finally back to 1. So this is how we get a happy number, is when we eventually return to 1. Now with this process, again called happy numbers, and we have a non-negative number that finally gets us back to 1. Now Fermat numbers are a long list, so we're going to talk about those a little bit later. Okay, so anyway, numbers are much more than sequences. Sometimes numbers can actually be shapes. So, like for example, if you take something that's not arranged in a sequence and put it into a shape, like to understand this, what I'll do, what I mean by shape, is I'll take an example of a triangular number. So the triangular number, these are numbers which can be arranged in the triangle. For example, T1 is a triangular number, 1. So I'm only going to consider 1 dot, and that is a number, right? And then we have T2 is the sum of, right? Take a look at this. It's going to be the sum of the consecutive natural numbers. So here, if I add 2 more dots, and this 1 dot is previous, I'm going to add 2 more dots with that, and I'm going to add as a triangle, or T3. Now the next triangular number is the sum of the consecutive numbers plus number 1 plus 2 plus 3. And I'm going to get 1, 2 dots. And this is because 1 and 2. And then I add 1, 2, and then 3. So I'm going to get 1 more triangle. It's a lot, I know. So the numbers which are arranged in this shape, of the triangle are called triangular numbers. I know that's really quick. More on these later. So anyway, these are triangular numbers. Remember, numbers can be shapes. We also got pentagonal numbers, hexagonal numbers, and so on. But the question is, who started observing and making these numbers so important and finding the applications of these numbers? So there's a list of numbers that we've been working with. And, we go back to the history and we can search back. One of the numbers that have been observed in the early ages, and it has a lot of applications, is the prime numbers. And if we take, as we can see that we have major 2 results, one fundamental theorem of automatic, which says that a number B, in the least if it is measured by a prime number, or can I say an integer n, can be factorized into prime numbers. And to find out, we can apply a Euclidean algorithm, and we can repeat the application of this to allow us to write a number into its own product of the prime numbers. Now, these 2 results are really important in the investigation of the different properties in these, subject number theory, in the subject of number theory, or we say in the subject of higher, arithmetic, we can get the opportunity to search the prime numbers. We know that there are only even prime number, or there's only one, and that is 2, and the remaining prime numbers are odd. So I can split this into classes. Let's say all the prime numbers are in the form k plus 1, or for k plus 3. The both are odd prime numbers, so we may want to know, what are the classes for k plus 1. Prime is equal to 4k plus 3, so it allows us to investigate the properties based on these prime numbers, and not to say, most of this proves, the prime numbers, are due to contradictions. So we'll be learning how to write, a formal proof using contradictions and a little bit later. Now, one thing about theory is talking about congruence is we have mathematics as the queen of science and number theory is the queen of math. This is Charles Gauss. And he introduced the symbol that we use and we know as congruence. And it's denoted by this equivalent that you see here. So this has a close analogy with algebraic equality, right? When we say that A is congruent to B modulo n, if n divides 2 minus b, because of this analogy and the resemblance of the symbol, we can approach divisibility. Now, we can approach the divisibility question through the arithmetic of the remainder of the arithmetic, where we can take an integer and have a binary or a decimal representation system. For example, I may write a capital integer n in the binary representation form, so I can write this in the form of a base that is 2, or base 2, or maybe I can have some other basis like b, and allow us to write down the number into binary numbers, or a binary number system. We can look at the theory to solve linear congruence, and this is similar to what we solve it as a linear for linear equations. Now, I have this equation, or I may write this as ax congruent to c modulo b. We can apply congruence to solve something in very large terms. Say I want to know this 2 to the power of, let's just say, 1,000 is congruent, or what is the last unit place of this number. So I can consider this intro into modulo 10, and then I consider what is a unit digit of this big number. So it allows us to solve a large number, and it allows us to find out what the remaining residual is here. So once we learn the linear congruence, we could find out the system of linear congruence solution by learning what the remainder theorem is. Now, let's talk about Fermat. So basically, he was a lawyer by profession, and he provided an elegant results. One that is the first Fermat, which says, like, for example, if P is prime and A is any integer where P does not divide by A, then A raised to the power of P minus 1 is congruent to 1 modulo P. That's a lot. And Fermat's latest theorem, which says x is 2, power to n raised to y to the power is equal to 0, is 2 has no integral solution when n is greater than 2. This problem was unsolved for about 100 years, but now it was solved by a proof given by Andrews. And while he has provided twice that the proof was incorrect the first time, and then recollected it again many years later, but it took many years for people to explore what could be the possible logical argument for giving the justification of why there is no integral solution to this particular problem. We're also going to talk about a little bit about the contributions of Euler. Euler contributed a lot to mathematics and also a lot to number theory. So I'm going to take a look at what Euler's theorem is in number theory and who he extended the formal theorem that we just talked about. Not to raise a power to P is congruent to 1 modulo P, But in fact, we're going to have to raise to the power of c, and that's congruent to 1 modulo n, where we have n as all those numbers which are relatively prime with n. We're going to talk a little bit about quadratic residues, and we can explore what I talk about the criteria to check a quadratic residue. Also, we're going to cover a thing about primitive roots, and as an application number theory. This is really a fundamental course that's used for the encryption and security issues within the next century we're coming into. So what we're going to do is within number theory, we're going to talk about kind of the basics of number theory. We're going to also talk about prime numbers and how prime numbers play a vital role in our daily life, such as encryption, and also talk about how we have various contributors to number theory and how number theory kind of built on itself and becomes relevant even to this day. So thank you for listening. I know that was a lot. I tried to kind of squeeze it all into just a very, very short video so you could kind of maybe maybe stop and then review exactly what we said. And, sometimes I stumbled over it a little bit. So just kind of look at what I have here on my board, on my video screen here. And if you have any questions, you can reach out to me. Thank you for making it this far, and I bid you all a very well rest of the day. Thank you.